Every powerful machine begins with a simple instruction. But inside a quantum computer, even the simplest instruction follows rules unlike anything in our everyday world. Our modern technology is built using tiny switches called bits. Every calculation, every game, every website begins with only two possibilities, 0 or 1. Logic gates are the building blocks of every classical computer. They decide how information moves and how every decision is made. But some problems become so complex that even the fastest supercomputers begin to struggle, requiring unimaginable amounts of time and energy. But what if computation didn't have to follow only zeros and ones? What if nature itself offered an entirely different way to process information? Welcome to the quantum world, where information is no longer stored as ordinary bits. Extraordinary objects follow the remarkable laws of quantum mechanics. Unlike a classical bit, which can be either 0 or 1, a qubit can exist in a combination of both states at the same time. This extraordinary property is called superposition. Scientists often visualize a qubit using the block sphere. Instead of being limited to just 0 or 1, every point on the sphere represents a unique quantum state. To perform useful computations, we must precisely change the state of a qubit. These transformations are performed by quantum gates, the fundamental building blocks of every quantum algorithm. Just as classical computers use logic gates, quantum computers rely on quantum gates, the fundamental instructions that control every qubit and every quantum algorithm. The simplest quantum gate is the identity gate. It performs no change at all, allowing the qubit to continue exactly as it was. The Pauli-X gate acts like a quantum version of the classical NOT gate. It flips the qubit, exchanging 0 with 1. The Pauli-Y gate also flips the qubit, but introduces a quantum phase using the imaginary number I, making it fundamentally different from a classical operation. Unlike the X gate, the Pauli-Z gate doesn't flip the qubit. Instead, it changes its phase, a uniquely quantum property with no classical equivalent. Perhaps the most famous quantum gate is the Hadamard gate. It transforms a definite state into a balanced superposition of both possibilities. A superposition is not a random guess. It is a precise mathematical combination of quantum states described by probability amplitudes. Every single qubit quantum gate can be understood as a precise rotation state vector on the block sphere. Every quantum gate is a unitary transformation, changing a qubit's state while perfectly preserving the total probability of the quantum system. Quantum algorithms are created by combining many gates together, each one carefully transforming the qubit step by step. So far, we've controlled one qubit at a time. But quantum computing becomes truly powerful when multiple qubits begin working together. The controlled NOT gate links two qubits together. The first qubit controls whether the second one changes, making interaction between qubits possible. Combined with the Hadamard gate, the C-NOT gate creates one of quantum physics' most remarkable phenomena, entanglement, where two qubits behave as a single connected system.
Every quantum algorithm is built from sequences of quantum gates, each carefully transforming qubits into the desired computational state. Inside a quantum computer, each gate becomes a precisely shaped microwave pulse, controlling fragile qubits with extraordinary timing and accuracy. Gate symbols are mathematical abstractions, but real quantum hardware performs them using exquisitely precise physical interactions with each qubit. Classical computers process bits with logic gates, while quantum computers manipulate qubits using quantum gates, enabling entirely new ways to process information. These quantum gates power technologies that could transform medicine, artificial intelligence, secure communication, and complex optimization. From simple state changes to powerful quantum algorithms, every quantum computation begins with these remarkable quantum gates. Understanding quantum gates unlocks how quantum computers process information and solve problems beyond the reach of classical machines. Quantum gates are far more than mathematical operations. They are the language that transforms quantum physics into computation.